Understanding how biomarker distributions evolve over time is a central challenge in digital health and chronic disease monitoring. In diabetes, changes in the distribution of glucose measurements can reveal patterns of disease progression and treatment response that conventional summary measures miss. Motivated by a 26-week clinical trial comparing the closed-loop insulin delivery system Slim X2 with standard therapy in children with type 1 diabetes, we propose a probabilistic framework to model the continuous time evolution of time index distributions using continuous glucose monitoring data, CGM, collected every 5 minutes. We represent the glucose distribution as a Gaussian mixture, with time-varying mixture weights governed by a neural ordinary differential equation, Neural ODE. We estimate the model parameters using a distribution matching criterion based on maximum mean discrepancy, or MMD. The resulting framework is interpretable, computationally efficient, and sensitive to subtle temporal distributional changes. Applied to CGM trial data, the method detects treatment-related improvements in glucose dynamics that are difficult to capture with traditional analytical approaches. To begin, let's clarify what we mean by a distribution in this context. In classical statistics, we often summarize data using means or medians. But in modern digital health, where we collect thousands of glucose readings per day, these point estimates lose critical information. Instead, we want to understand the full shape of the distribution, how often glucose levels are low, moderate, or high, and how that shape changes over time. This is especially important in pediatric type 1 diabetes, where children under 6 face unique challenges: unpredictable eating patterns, small insulin doses, and high glycemic variability. Standard metrics like mean glucose or time in range are useful, but they don't fully capture the richness of the data, particularly short-term fluctuations and the rate at which glucose levels change. Our goal is to model the continuous evolution of the glucose distribution across time. Let ft, x, denote the cumulative distribution function of glucose at time t, and let ft, x, $ be its density. In practice, we observe data only at discrete time points, every 5 minutes, so we must infer a smooth, continuous time representation of ft $ from these snapshots. We model ft as a Gaussian mixture with k components. ft, x, equals \sum s equals 1k \alpha st \mathcolen, x \mid ms \sigma s. Where ms and \sigma s are fixed across time, the shared dictionary of latent glycemic regimes, and \alpha s, t, $ are time-varying mixture weights that evolve continuously. This structure assumes that the underlying metabolic states, like fasting, postprandial, or hypoglycemic, remain stable, but their relative prevalence shifts over time. Why a Gaussian mixture? Because it balances flexibility and interpretability. With just 5 components, we can capture diverse glucose patterns, such as stable normoglycemia, rapid drops, or prolonged hyperglycemia, while keeping the model transparent. But how do we estimate these weights over time? We use a 2-stage approach. First, at each observed time point ti $, we fit a static Gaussian mixture to the empirical data using maximum mean discrepancy, MMD. MMD measures the distance between 2 distributions by comparing their embeddings in a reproducing kernel Hilbert space. For a Gaussian kernel, this leads to a closed-form objective. \text MMD2, \muti, \nu \theta I, equals \alpha I top I \alpha I2 \alpha I top ji plus ci. Where \muti is the empirical distribution of glucose readings at time ti $, and \nu \theta I is the fitted mixture. The matrices II and ji $ depend only on the data and the component parameters, allowing efficient optimization. We initialize the component parameters via k-means clustering across all data, then alternate between updating the weights via quadratic programming and refining the means and covariances using gradient descent. This ensures a stable, data-driven fit at each time point. Second, we smooth the discrete weight estimates into a continuous time trajectory using a neural ODE. The neural ODE models the evolution of the weight vector \alpha t as \fracted tz, t equals v \phi z t, t \quad z 0 equals \alpha 0, where v \phi $ is a neural network parameterized by \phi. The solution z, t, $ is mapped to the probability simplex via a softmax-like normalization. \alpha t equals \frac zt plus \langle 1 zt plus \wrangle, ensuring valid mixture weights. This approach has several advantages. It naturally handles irregularly sampled data, common in real-world CGM, without requiring interpolation. It produces smooth, differentiable trajectories that reflect biologically plausible changes in metabolic state. And because the component parameters are fixed, there's no permutation ambiguity. Component 1 always corresponds to the same glycemic regime across time and individuals. Now, let's turn to the results from the clinical trial. We analyzed data from 102 children aged 2 to 5, randomized to either closed-loop therapy, Slim X2 with control IQ, or standard care. The primary outcome was not just mean glucose or time in range, but how the full joint distribution of glucose and its rate of change evolved over 26 weeks. We used a bivariate model, glucose level and its first derivative, rate of change. This allows us to detect not only shifts in average glucose, but also changes in glucose dynamics, like whether the system is more stable or prone to rapid swings. Figure 2 shows the estimated weight trajectories for the 5 components. In the treatment arm, we see a gradual increase in the weight of component 1, a favorable regime characterized by glucose levels around 100 mg/dl and near zero rate of change. Meanwhile, the control arm shows little change, or even a slight decline in this component. Conversely, component 2, associated with higher glucose and positive rate of change, gains weight in the control group, suggesting more frequent postprandial spikes. In the treatment group, this component remains relatively stable. These patterns are not just descriptive, they're statistically significant. Using a wild bootstrap MMD test, we found that the difference between arms becomes significant for components 3 and 4 by week 20, and for component 1 near the end of follow-up. The p-values, figure 4, show a clear temporal signal. The treatment effect accumulates over time rather than appearing immediately. But what's even more telling is the heterogeneity of response. Figure 5 reveals that while the median trajectory stays near zero, the interquartile range widens over time. This means that only a subset of children, those who respond well, show a strong shift toward favorable regimes. The rest remain largely unchanged. This is crucial. It shows that the intervention isn't uniformly effective. Instead, it benefits certain individuals more, likely those with better adherence or more predictable lifestyles. This insight is invisible in traditional analyses that average across the cohort. Figure 3 visualizes the bivariate density evolution. In the control arm, the distribution shifts slightly but inconsistently. Positive and negative changes cancel out. In the treatment arm, however, we see a clear redistribution. Mass is transferred from high glucose and high rate of change regions toward a narrow band in the mid to high glucose range with near zero dynamics. This suggests that closed-loop therapy reduces both hyperglycemic excursions and rapid fluctuations. Moreover, the different surface in the treatment arm shows a strong positive band in the mid-range, with compensatory negative regions elsewhere, indicating a systematic reorganization of the joint distribution. This is not just a shift in location, it's a transformation in the underlying metabolic state. So what does this mean clinically? First, the closed-loop system improves not just glucose levels, but the dynamics of glucose regulation. Second, the benefits are not immediate, they emerge gradually over weeks. Third, the response is heterogeneous. Some children benefit dramatically, others only slightly. This supports a personalized medicine approach. Rather than treating all children the same, we should identify those most likely to respond. Compared to conventional methods, this framework offers a richer, more nuanced view. It captures both the distributional shift and the temporal dynamics in a single, interpretable model. It reveals patterns that standard summaries miss, like the stabilization of glucose fluctuations, which are critical for reducing long-term complications. In fact, this method is more than just a tool for diabetes. It's a general-purpose framework for modeling any time-varying distribution in digital health, from accelerometry data in aging populations to fMRI signals in neurological disorders. The shared dictionary Gaussian mixture with Neural ODEs smoothing provides a powerful balance of flexibility, interpretability, and computational efficiency. And while we've focused on glucose, the same principles apply to any biomarker that evolves over time. Heart rate variability, respiratory patterns, even sleep architecture. The key insight is that the distribution is often more informative than the mean. In conclusion, this work demonstrates that continuous time modeling of probability distributions, through MMD-fitted Gaussian mixtures and Neural ODEs, can unlock deeper clinical insights from dense, longitudinal digital health data. It moves beyond scalar summaries to reveal how physiological states evolve, how treatments reshape them, and how individuals respond in unique ways. This is not just a statistical innovation, it's a paradigm shift in how we understand and analyze health data. And as wearable sensors become more widespread, methods like this will be essential for turning raw data into actionable, personalized medicine.